My name is Lydia Martinez, and along with Kaylin Younger, we are Team MEDi Tech, and I will be going through a video manual of the digital pathology slide scanner that our team developed this semester. The goal of our design for the slide scanner was to create a low-budget system that securely holds multiple glass slides, supplies consistent illumination for imaging, enables X, Y, and Z axis movement of the main imaging components to, of course, produce high-quality, consistent images of pathology slides. We also wanted our system to be semi-automatic for minimum user input. Here is our full assembly. The brains of our slide scanner is a Raspberry Pi 4, which is connected over USB to an Arduino Uno. A CNC expansion board is attached to this Arduino, which allows the Raspberry Pi to send G-code commands directly to the stepper motors over serial. Our optics module includes a Raspberry Pi HD camera, a tube lens, and a 20x objective. The stepper motors control the Z, X, and Y movement of the optics assembly. And finally, LEDs are mounted directly underneath the slide holder to illuminate the slides above, with a potentiometer knob to control the brightness of the LEDs. I will now go through instructions for how a user would use our slide scanner. Here is the MEDi Tech DPSS system, already mostly pre-assembled in Wyman Park. The slide holder is already attached with 4 bolts at each corner of the gantry. The optics module is already bolted to the Z-axis mount. As you can see here, this can move up and down, back and forth, this way. Slides are inserted starting here as labeled, slide 1, moving this way, down to slide 6, moving back. This is because of how the program was set up that will take the pictures of each slide. Here we have the illumination, which is connected underneath the PCB, and then the Arduino and CNC shield. So to get started, I already have the Pi turned on. That would just be with this switch. And I have the motor plugged in as well, the motor power. To turn on the illumination, we do the same thing here. Plug this in. You see, plugged in. And we turn the knob to change the brightness. So now they're fully bright. And the slide, which I already inserted one, is illuminated. And we can place another one here. So now that everything is set up, everything is powered, we want to open the MEDi Tech DPSS program. Pathology is probably the easiest way to do this, so you can kind of see what's going on and track if there's any errors. So here's the program on the screen, and then you would hit run and the program would start, as will be shown in the next demo. Once everything is done and all the slides have been imaged, then you can power off the LEDs and unplug that. and unplug the motor. So there's no power to anything. And then of course, shut off the Pi. All the images are stored on the Pi, but the Pi is configured to be remotely accessed, so you can access those images remotely or just by opening them in the folder here. And here is a demo of our slide scanner in action. Via remote desktop control, Kaylin just started the scanning program on the Raspberry Pi. It is set to move the optics module 1 millimeter in a snaking pattern across the slide, as you can see here. G-code command is being sent directly from the Raspberry Pi to the Arduino, which then controls the stepper motors. And there's that Arduino with the CNC expansion board. An image is taken about every second, and for this sample size, it'll take about 500 images to image the entire sample, which is a little under 9 minutes for one slide. Here we are only imaging one slide for this demo.
Hello, I would like to do an example of the image stitching program. So to begin, we have our own separate environment for the image stitching because it runs OpenCV on an earlier version of Python. So I'll activate that virtual environment, and then I can move to the location where I want to save the file. So this would be any folder that we want to save the correctly stitched image. So we're just going to move to this files folder for OpenCV. Then here we have the path to the file we want to stitch. So this is a folder and it has example images. So if I show files, these are a bunch of images and they're saved chronologically in order, like how our Python code saves images in the order that they were taken. So for this example, you'll then input parameters about the stitching that needs to happen. It will ask how many columns. It will ask how many columns the tiles make. And then also we can say if it's snaked or ratcheted. And after confirming, it'll define features and key points that are found in each of these images. The problem that we've been having with this program running with the images taken with our digital pathology scanner has been that there are not enough key points found. So now that this mosaic is complete, we can see that there's this new example2.tif. So with that, we can open a new file to see that it's a successfully stitched image. And if we were to compare it to one component of an image before, we can see that this was put here. There are very few lines between the images just because this sample has a lot of key points.
From this demo and similar tests, the key results are as follows. At full capacity, we can image 10 slides due to the fact that there are 10 slots in our slide holder. One image is taken every 1 second. So for a 35 by 15 millimeter sample, we would be taking 525 images at 20x, which is 9 minutes to image one slide. It then takes 10 to 15 seconds to stitch images for that slide. And then another key result is that there's consistent lighting between the slides. There are also some limitations of our system. As you can see from these images, the edges are not sharp, and this is largely due to the focal plane of the camera sensor being between the objective lens and the optics module tube, instead of between the objective and the surface of the slide. This occurred due to the addition of an IR filter on the camera, changing the distance between the camera sensor and objective. This can be corrected by shortening the length of the 3D printed optics mount. Our illumination should also be brighter. The LEDs that we bought dimmed through use and should be replaced with higher quality LEDs to improve the image quality. And lastly, another limitation is that we have manual image focusing. Currently, the user must input the Z-axis position in the code manually. A GUI would help with the ease of use of this part of the process. In summary, MEDi Tech's low-budget digital pathology slide scanner costs less than $800, images a slide in a little under 9 minutes, can hold up to 10 slides, is semi-automatic, has robust access translation, and is extremely modular, so it's easy to replace components if they need to be upgraded or they somehow break. Thank you so much.